This is for those who believe in the potential of science, making brave choices, choosing to push the boundaries. This is why we believe in what science can do.
How are you guys? Awesome. So today I want to teach you nothing amazing, but just show you pictures of what our universe can look like. Now, I'm a math professor, so you have to nerdify it up a lot, right? You just can't show pictures about the universes, but I want to show you how to build new possible universes. So the way to do that, it turns out if you actually think about it just for a little bit, is that we're actually not mature and strong enough to lift such a box. So we have to work on our muscles to get to that point of understanding how to draw those shapes. In order to do that, I want to talk about the Earth. But let me show you one thing first. The goal of sort of what today's activities are in many of the talks you guys have maybe gone to is to get you guys excited about science and math and engineering and technology. Here's what I want you guys to get out of it from my talk. Learn to draw. That's it. Many of you guys might be thinking, wait, what does this have to do with the next revolution? I'm already a good artist. It turns out you're not, just to let you know. What does this have to do with being a great computer scientist? I want to go to Stanford and write the new computer code that's going to take over Google. That's awesome, right? But if you think that your mind can be broken up into a piece that just does mathematical stuff, without the side that has to do with artistic stuff, you will not be the revolutionary person you want to be. So my encouragement for you is to think about it in a holistic way. It's to use your hands, right? Sculpt things in clay, and you will never imagine how that's going to help you in your career, how that's going to make you a better artist, a better mathematician, a better computer scientist, better engineer. Even Frank Morgan, the professor who was right here before me, he talked about blowing bubbles, soap bubbles, and how that has to do with the most cutting-edge architectural design and issues in cell biology out there. And you would never think blowing bubbles as a kid has to do with these things, but it does. So my thing I want you guys to walk out of it is don't cut up your mind into pieces. Learn to draw, and that will influence you in ways you will never realize. All right, there's my little speech. But let me tell you this way of thinking about the universe. Instead of thinking about the universe, first, here's what I want to think of in the beginning. I would love for us to talk about just the Earth. What is the shape of our Earth? It's awesome. Let's break it down, all right? So there's your Earth. Now, what are the properties of the Earth that we know are true? Here are a couple of things that I believe we know are true, all right? First of all, we think it has limited area. Now, before, olden times, people used to think, you know what? If you actually think about the shape of our Earth, if you actually go outside and look at it, it looks flat, right? And actually, it looks flat that it seems to be going on forever. And in fact, no matter where you're standing, it seems to be going on forever. So you would think it was just a plane that just goes on forever. But we now know that that's not true, that nothing is that big. The area has to be limited. This is why you have to pay money to buy land, because there's only a certain finite amount of it. So we know that the Earth has to have limited area. All right, here's something else we know. Does it look like this? Now, why isn't it? Whoa, first of all, check it out. Does it have limited area? Yeah, so what's so creepy about it? Does it look flat? If you go outside right now, if you go outside and check out the Earth, doesn't it look flat? So why isn't this the shape of the Earth? Yeah, thoughts? It's three-dimensional. Let's talk about dimension just for a second. The surface of the Earth is only 2D. Do you guys believe that? And here's why. Don't you only need two numbers to tell anybody where you are on the Earth? Longitude, latitude. So the surface of the Earth is only 2D. Doesn't that only have an X, Y coordinate thing? You only need two numbers to tell somebody where you are? It seems totally cool to me. Why does this make your stomach turn? It's not because you know the right answer. It's some other reason. Any thoughts? Yeah? Not gravity. Those are all okay, that's a great answer. Physics nerdiness. I'm a math guy. Don't do that. That's great, though. I love it. Thoughts?
The clouds are thicker than the Earth.
Again, clouds, biology, chemistry, not interested. That's a great answer. Love it. You guys are way smarter than I am. I'm just a lowly mathematician. Yeah, thoughts? There it is. There's the money, right? It looks flat, which is great, but there's one weird thing about it. There's something called the end. Do you guys feel that? That you could actually go to the end of the Earth and fall off? Now, that makes us really Creeped out. So here's the second rule. There is no end. There's a never-ending earth. If you're going to build the earth that we have today, here are the two rules you got to have. One, limited area, right? You can't just do it forever. And two, there can be nothing called the end of the earth. People used to think that the earth had an end, right? They used to have warnings, sailors, be careful, don't fall off the edges. In fact, in Scripture, it talks about God sending the angels to the four corners of the earth, the edges of the earth, talking about God's full power over everything. So we know that the earth has no infinite area. We also know that it has no end. So we have to have these rules. Because of this, now we can talk about the shape of the earth. Now, do you guys believe that this shape right here satisfies both of those properties? Do you guys believe that the amount of area you have is finite? Totally cool, right? And does it have an end? If you keep walking and walking and walking, do you ever come to the spot that says, dude, I'm right here at the end of the earth? No, it just keeps going, right? Now, you might not be able to get to the Antarctica. It might be tough, but still, when you keep walking, you never come to the edge of the earth. Now, here's my question. Why can't this be the shape of our earth? Check it out. This is a math person, right? There's this physics world of astronomical gravitational pull. I don't know what those words are. There are clouds. I don't even know what a cloud is. Not interested. From a math nerdy perspective, right? Just from these two rules, does this donut shape have finite area? I wish a donut had infinite area for the amount of glaze that can go into my body. But unfortunately, finite area, that's true. Secondly, does the donut have an end? No, because if you keep walking, you come to the other side, you keep rolling this way, you keep inside and out, right? So this satisfies those two rules of what it is. Now, here's another rule. Check this out. What about this guy? Does this satisfy these two rules? Yeah. So you guys can imagine something with 2 holes and 3 holes and 4 holes. All of those guys could have been the shape of our earth. Now, why do we know that's not it? Thoughts? Gravity, love it. Yes, awesome. Gravity's going to pull you into some kind of a spherical thing, yeah?
Yes, also because of gravity, but a different logical reasoning.
Yes?
When the Earth was created, it was just small particles.
Okay, he's saying the wind, when it was first formed, it kind of pulled this way. Thoughts?
The mantle inside, it was hot.
Man, you guys are total physics brilliance over here. I don't know those words. I love it. Love it all. Let me give you a couple of snapshots, right? And I'll keep going. One, how do we know? How do we know? Number one, here's one, right? We've been everywhere. We can actually draw the earth itself, right? We can actually trace every spot out there by us as humans physically traveling to those spots. Any other reason we know without any physics? Thoughts? Yeah. There you go. We left it, right? That should be, by the way, number 2 for those guys. We've explored the earth, and we've actually left the earth. Do you guys see that? Those are the 2 reasons we know it's this. We can actually leave it and check it out. So now, that's the basic setup for what the earth is for us to think about it. Now, here's my question for us. Today, what I want to do is get you guys excited about thinking about the universe. All right, what do we believe? Now, there are a lot of physical rules. Now, when it comes to the things like the universe, all the rules about physics, about gravitational pull, we think we know, but we're going to be a little fuzzy about. So here are the 2 rules we're going to set up that's going to look exactly like the rules of the earth. Rule number 1, it's going to have limited volume. So you would think, if you look outside the universe, everything that's out there, that's the definition of the universe, by the way, everything that's out there, right? If you look outside, you would think, oh, it just goes on forever. But that's like the old way we used to think about the earth. Isn't that true? We used to think that the earth was flat and goes on forever, and we matured beyond that. So I know that the universe, because of the amount of energy that was taken to start the Big Bang and all these kind of, had limited volume. There's only a certain amount of stuff that's out there. You just can't say it goes on forever. That's rule number 1. Here's rule number 2. It is never ending. Just the way that the earth does not have an edge to it, does not have a place you can come and fall off. Now, here's my question, my friends. Can you guys think of one example of an object that is 3-dimensional, now you can fly, right, because you're talking about the universe, that has a limited amount of volume and it has never an edge to it, never ends to it? Thoughts? Yeah. Orange shirt. A sphere? Yeah, a sphere's good. Maybe, let's take a look. Look at these shapes we talked about last time, right? Now, the problem these guys, we can't use these as our universe is the following thing. A universe is 3D, right? You just can't have longitude and latitude. We got to fly around the universe. What happens if I take a ball, like this one, and fill it with water? Or fill it with volume, right, something, and put my spaceship inside it and make the ball really huge? Does it have finite volume? Yeah, because it's in a ball. I'm holding it in my hand, right? And the spaceship can fly in there, finite volume. Here's my second question. Is there anything called the edge of that ball? There is. If you're flying inside it, you could actually come to the edge of the sphere and say, I've come to the edge of the universe. That's exactly like coming to the edge of a disk and saying, I'm come to the edge of the earth. Didn't that look silly to you when I showed you that flat disk? That's exactly how silly it should be for you to think of a sphere with stuff in it. So we know that can't be the shape of the earth. So here's my question. What possible shapes can the universe be? How do we even do this? This is what I want to show you today by just drawing pictures. Two problems. Even if we can think of cool shapes of the earth, here are two problems for us. Problem number one, it's way too big to explore. We can't actually go everywhere the universe is like we did for the earth and figure out what it's going to look like. And here's the second problem, which is even worse. You can't leave the universe. You could leave the earth and check it out, but you can't leave the universe and check it out. So we have to try to figure out the shape of the universe without checking it all out and without even leaving it. But before we even get there, we don't even have a possible way one shape can be. Can you guys think of one shape that's finite in volume but has no edge, has no end to it? And let me tell you this, the reason no hands are going up is because it's really hard. Just coming up with one shape, anything you think of to put volume in, you got to have a box to hold it. And the moment you got the box, you got the edge of the box. So now here's our problem, and here's the way we're going to solve this problem. You guys ready for this thing? We're going to multiply. Simple multiplication. Now, here's my question. First time, 3 times 5 is? How did you do it? What did you do? Nobody multiplied in this room. Here's what you did. You vomited the answer out that was stuffed into you in 2nd grade. 7 times 7, what is it? 49. Yeah, right, you're multiplying 7 times 7 to get 49. You're just vomiting it out. Nobody knows a thing about multiplying. You're just memorizing those things. Do you think you really added 7 plus 7 plus 7 in your head that fast? No way. Pure memorization. So let's break it down and tell you guys what multiplication is. Now, I love to draw. I told you guys that's one of the first slides I put up, learn to draw. So I want to show you guys multiplication from a pictorial setting. 3 times 5, let's check it out visually. 3 times 5 means 3 dots, 5 dots. Here's what multiplication is. For each one of those dots in 3, you give it 5 things. Boom, 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 boom. Cool? Visually, that's what's going on. For each one of those things, you give it 5 things. So which means for each one of that, you give it 5 things. For each one of that, you give it 5 things. In total, you look at the number of red dots there are, you got 15. Cool? Now, that's not amazing. You guys know that's how 7 times 7 works, or 8 times 5. You know, for each one of those things, you give it the set of all things. That's how you multiply numbers. The same identical trick is what you use to multiply pictures. Now, a number times a number is a number, and a picture times a picture is a picture. You can build new numbers from taking old numbers and multiplying them, and you could build new pictures and new shapes from taking shapes you know and multiplying them. So here's what I want to do. I want to build for us a shape of the universe by multiplying. Let's start with this. Simple multiplications, 2 lines, right? 2 line segments. You take this guy, you multiply it. How do we do it? Here's what we do. For every point on that line segment on the left, I give it an entire line segment. Just like for every 3, you give it a 5. Isn't that what we did for 3 times 5? So for that point right there, I give it a line segment. For that point right there, I give it a line segment. For that one, I give it a line segment. For that one, I give it for every point, I give it a line segment. If I do it for every one of those points, what do I get? You get a box, you get a square. Perfect, right? So for each one, I give it an entire line segment. You can imagine the whole thing smearing and getting shaded, and you get this square, this rectangular box of possibilities. So a line segment times a line segment is a square. Cool? All right, great. Now check it out. Here's what I want to do. I want to turn it up a little bit. The problem with line segments is they have edges to it. Does that make sense? Do you guys see you got these ends to it? And do you guys see the problem with those ends is that now the square has ends to it, because it inherits the properties of the line segments. We don't want things with ends, right? Our goal is to build a universe without an edge to it. So let's start with things that have no edges, circles. Circles, there's no place you can fall off. You can just keep going. So what happens, instead of a line segment times a line segment, I decide to multiply two circles together. All right, let's check it out. Now, for each circle, for each point on that circle, I need to give it another entire circle. So a circle times, now you can say things like circle squared, but that's like a math lingo, right? That's like a notation to keep. I want to draw. I want to visualize what this thing is. So here's what we do. We cheat. Have you guys ever played Super Mario Brothers? You know in Super Mario Brothers, there's those green tunnels you can go down, those tubes? It's like a warp zone, and you come out in a totally different spot. That's what I'm going to do. So I take the circle, I put a red dot in it, and I cut it open. Now here's the catch. This thing looks like a line segment, but it's really a circle because those two red dots are the same. It's like a warp zone that goes from one to the other. So if I walk all the way up and I get to the top, I come back to the bottom again. That's that warp zone. That's a circle. So here's what I'm going to do. Circle times a circle. I take this guy. I'm going to multiply it by this guy, putting a green dot and ripping that open. So doesn't this look like a line segment times a line segment? We just did this problem. So this guy is just the box we talked about. But here's the catch. This is not a line segment. This is a circle. So those two ends are the same, which means anything touching those two ends are going to be the same. So that red thing, those two red lines are going to be identical. They're the same red line. It's not two separate red lines. They're the same ones. And these two green lines, they're the same green line. Make sense? Now, what happens if you're a person living in this amazingly weird box I've created? There you are, you're walking. What happens when you hit the right wall? Boom, you go to the left side. It's the same wall. Do you guys see that? Because it's one circle. Do you feel the circleness right here going this way? Now, what happens if you're a person up here and you walk down? You don't come to the edge. Boom, you go back right there. Have you guys, this is old school, but have you guys ever played Pac-Man? That's this. Pac-Man is played on a shape that's a circle times a circle. That's where Pac-Man's played on. Now notice, there's no place you can fall off here. The moment you come to the edge of something, you disappear and you go back to the other side again. There's no place. Now, does this have finite area? Yeah, right there. Do you guys see? It's the amount of colored I have. It has finite area, no place to fall off. What is this visually? Well, here's the way to look at it. That's what I just drew for you guys. But we know that the two red ones are the same, so I can glue the two red sides together visually in my hand, glue it like this. You get a cylinder. But isn't it true that the top green and the bottom green rings are the same also? That means I can glue the two rings together, and I get a donut. Which means Pac-Man is being played on the surface of a donut. And that is why this thing has no edge, because a donut has no edge. Finite area, no edge. Now, nobody cares about this problem because you're here to talk about the universe. And I've just told you things about a donut, which we know is on surfaces. I want to do 3D. So here's my question. What happens if you do 3 circles? Circle times a circle times a circle. Now, if you think, thoughts? Tesseract, love that word. Way too hard for my brain. Small brain here, not that strong. Yes?
So when you have the rectangle,
yes?
it's going to be a 3D rectangle.
Yes?
What do you call it? It's not a cube, but it's a rectangle.
Yeah, so check it out. A line segment times a line segment is somehow related to a circle times a circle. A line segment times a line segment times a line segment is related to a circle times a circle times a circle. So you get something like this. You get a cube. Now here's the catch. Isn't it true that in the cube, these aren't just line segments, these are circles, which means if I go from this face to the back face, I reappear on the front. And if I go from the bottom all the way to the top, I reappear on the bottom. And if I go from left to the right, I reappear on the other side. Think about this just for a second with me, right? Here's what we believed about the universe, that this had limited volume. Does this thing have finite volume? Yeah, because I can hold this cube in my hand. And here's the second thing. Is this never ending? Well, think about it. If I'm inside that cube, and if I come to the face of one of those cubes, do I stop? I can keep going, and where do I appear? On the back face. Just like I walked on the square, and I walked this way, and I reappeared on the other side, just like the way Pac-Man does. Pac-Man doesn't die when he comes to the end. He just goes the other side. That's what happens. Now, here's my question, my friends. We have built something right here. Limited volume, Totally true. I can hold it in my hand, and it has no edge, which is amazing. So here's my question. How does it look like? If you're inside this object, and if you look outside, sitting in there, what does this world look like if this is your universe? Here's what it looks like. This is a program by Jeff Weeks, and it's a brilliant program called Curved Spaces. You can download it for free. And this is actually a program, if I had the power to do it and show you my computer, you can walk around and move in an animation. But these Earths that you see, they're not copies of the Earth. They're the same Earth. Because when Pac-Man looks ahead and sees a wall, that wall looks ahead and sees the back of his head. Because that's how light travels. So these Earths are actually the same Earth. In fact, if our universe looked like a box, like a cube with the sides glued together, you would get this. Now, instead of gluing a cube, that's what I did. What happens if I took this guy and glued it? You know, who said I have to have a cube as the playing field? Well, again, do you guys know the dodecahedron's like a dice you can play? Why don't I start with these guys and glue that pentagon up there to another pentagon down here and play this game? If I did that, here's what my universe would look like. Can you guys feel the difference? Just actually feel the difference? The first one, it felt like it kind of had lots of volume and you can kind of travel around. It was still finite, but it felt more spacious. This one is cramped, all right? And these Earths, by the way, are the same Earth. You see yourself in different mirrors when you put jeans on at the Gap. Right? That's what's going on in your universe. Now, if I take the same dodecahedron, and instead of gluing my pentagons like this, I glued it in a little bit different way. Instead of getting something called a Poincare dodecahedral sphere, I get something called a Seifert-Weber space. You get this. Same thing. And it looks still finite, but it looks incredibly vast. All of these guys coming from gluing, and here's what I want to close with. Here's an amazing math result. Every possible universe that you can want to imagine has limited volume, doesn't go on forever, and never ends, right? Just keeps going, can be made by gluing sides of any polyhedra you can imagine. That's it. If you want to build universes, take polyhedra and start gluing things together, and you'll get it. So let me just close with this. Learn to draw. It'll help you see things better. Thanks, my friends.